Alright guys, welcome back. We're going to be solving on a question from the third chapter of the Meriam textbook, Engineering Mechanics. And in this one, in a procedure to evaluate the strength of a tricep muscle, a person pushes down on a load cell with palm of his hand. So we're talking about this part, which the load cell reading is 160 newtons. So the question is asking us to determine the vertical tensile force F generated by the tricep muscle. And we know the mass of the lower arm is 1.5 kilogram, and we have a mass center in the figure, the point G that we can see in here, and we can state any assumption that we are considering in this question. So first of all, we are in equilibrium. So we have our equilibrium equations, which are sum of all forces in x equals 0, sum of all forces in y equals 0, and we're going to have one moment equation about any points, which means we can find up to 3 unknowns into the question. So as always, we're going to start with the free body diagram of this part. So we have a force that is applying from the load cell. That's going to be in this direction, and we know that's 160 newtons. It's a given in the question. We're going to have the weight of the lower arm, which is 1.5 kilogram, and we know weight is mass times acceleration of gravity, and we know our G is 9.81 meter per square second. And if we just multiply the mass based on kilogram by G, so 1.5 times 9.81, that's going to give us the force in newtons. So that would be our weight. At point O, we have some sort of a pin, which means we have two components, one vertical component and one horizontal. We can just call our X and Y in here. But keep in mind that what we are interested in here is the force that is applying to the triceps. So here, and the question is saying that the triceps is actually in tension, meaning we have these two forces, but that's the force that is applying from the lower arm to the triceps. The force that triceps is applying to the lower arm has to be in the opposite direction or this direction based on the Newton's law. So the correct direction for the force F that the question is asking would be upward, and we know the force is vertical. Again, it's part of the givens in the questions, and that's pretty much everything we have in this question. The rest of this is using these three equations to find the unknown in here. We are interested in F, which means if we just go straight with the moment about point O, counterclockwise positive, we can get rid of OX and OY, and we can find F in one shot, and we don't need to go through sum of all forces in X and Y. So we're going to have the moment of F about point O, which is in this direction, so it's a clockwise moment. So negative F times the distance would be the vertical distance to the line of action of the force, or 25 millimeter. I'm not going to do unit conversion for the distances that we have in millimeter because it will be cancelled out at the end. We have the moment of the next force or the weight. This one's also clockwise, so another negative moment, so minus the weight 1.5 times 9.81, and again vertical distance from the point O to the line of action, this time 150 millimeters. And the last one would be the force of load cell, which is going to make a counterclockwise moment, so plus 160, and the distance would be the distance from O to where the load cell is located, so 150 plus 150, or 300. This will be equal to 0, and our F would be basically 160 times 300 minus 1.5 times 9.81 times 150 divided by 25. So 160 times 300 minus 1.5 times 9.81 times 150 over 25, and that's going to give our force F 1831.7 newtons, and the final answer for this question. Again, the reason I didn't do unit conversion for millimeter will be just dividing each of these by 1,000, which won't make any change in this equation. Just have to multiply everything by 1,000, and we get what we had in the previous step. So yeah, that's pretty much everything. Hope everything was clear. Let me know if you guys have any questions. You guys take care. I'll see you in the next video. Have a good one.